Alright guys, so I sort of realized that there were a few topics that I forgot to cover in yesterday's video, so I thought I might quickly just do them here. Now, the first being this superdense coding. So superdense coding is a sort of data transfer or communication protocol in which it is possible to transfer two classical bits of information by um, transferring a single qubit of information. Now, here's the way it works. So you have Alice and Bob who share a entangled pair. Now they go each their own way. They maybe take their qubit to their own respective labs, and let's just say, for the sake of the thought experiment, that these two labs are very far apart. So we could say that like one is right here in Copenhagen, and the other is in Sydney, Australia, for example. Now, Alice wants to transfer two classical bits of information to Bob by giving him a single qubit of information. Now, the way she does this is that, well, she knows that her qubit is entangled with Bob's qubit. Now, she performs up to two unitary transformations. She has four possibilities, those being that she could do nothing to her qubit, she can apply x to her qubit, she can apply z to her qubit, or she can apply x and z to her qubit, both corresponding to, 0, 0, 1, 0, 0, 1, and 1, 1. That being for like x and z. Um, Now, once she's performed that unitary on just her qubit, she transfers her qubit somehow to Bob. A realistic way of thinking about this is just that it's light, which is being sent through like very high quality optical fiber. But again, for the sake of the thought experiment, let's just say that Bob receives her transformed qubit in a very well preserved manner. Now, Bob has both the qubits which are entangled. Now he performs a very unique type of measurement called a Bell basis measurement, meaning he doesn't measure in the computational basis, he measures in the Bell basis. Now this destroys the um, the entanglement, but it does retrieve the information. Now the reason this works is because when you perform a Bell basis measurement, you get one of four results corresponding to the Bell states. Basically, Bob finds out which basis it's in, and um, he can actually distinguish between all these four as they are unique depending on Alice's choice of unitaries. So I can't remember what exactly it was, but basically, like each one of these corresponds to, like, okay, this first one, for example, that just corresponds to if Alice does nothing to her qubits, which would be 0, 0. This one corresponds to if she performed a Z. So this is if she wanted to send 0, 0. This is if she wanted to send 0, 1, because she only performed her Z unitary on this. This one corresponds to 1, 0, because there's been a bit flip with no change in phase. And this one just, of course, corresponds to both of them. And we can see that Bob is able to distinguish these because the Bell basis tells specifically what Bell state it was in, which they sort of sum up in this figure right here. Now the way these two different gates work is that the Pauli X gate it takes the zero state or the computational zero state and transforms it into the computational one state, and vice versa. Uh, Practically, what this means is that it's just the quantum bit flip gate. Now, the Z gate is very unique to quantum because this doesn't affect the zero state, but it changes or it flips the phase on the one state. So this is the phase flip gate. Now, something to notice, which is pretty cool from this, is that a Bell state can be changed globally by applying only a local unitary to one of the qubits. Now, let's look at an example of uh, a bit that Alice might want to send. So if Alice is interested in sending, say, I can't remember. Okay, 1, 0. Hold on just a second. I might have messed this up actually, which is pretty funny. But still, let's see how like one of these gates work. So like if you were to practically calculate what it's like to apply a single gate to a joint system, you might express it as such, where oh, okay, now I realize what it is that I did wrong. I accidentally picked a random state when you aren't supposed to. Okay, I chose to start out with this state when I should have started out with this state. My bad. Um, the protocol works, but this is just like an example calculation. So if Alice has the state psi negative, which corresponds to this state right here, which we can see right here, and she wants to flip uh, her part of the bit from this joint system, the way we express it is via this tensor product of operators. Because it's only Alice's qubit which is being affected, we tensor, um, she wants to bit flip it. She performs a Pauli X gate, and we have to mathematically express this as the Pauli X gate tensored with the identity, because Bob's bit doesn't change. Now, this has to be applied onto the state, the superposition. This like tensor of an operator, we can consider one entity because the kets right here are actually also tensors of two different qubits. So we can like move it as if it were one entity. So move it in front of this, move it in front of this, and it will end up looking like this. Now we can, I didn't bring it up here, but if you remember the identity I showed in the last video, where you have tensor products multiplied with tensor products. The first element of the tensor product matches with the first, the second with the second, the third with the third, etc. Meaning the x gets matched to the 0 here and the identity to the 1, and over here the x gets matched to the 1 and the identity to 0. So we'll end up looking like this down here. Now we just sort of evaluate. So x applied to a ket 0, that becomes a 1. The identity applied to a 1 just becomes a 1. The ket applied to a state 1 becomes 0, and the identity applied to a ket 0 becomes 0. Now, this state we see right here is something we recognize, almost. So notice how there's a negative sign here and no negative sign outside. Well, what if we sort of just, pull out this negative sign, so flip it on the entire thing? We can express it as negative multiplied by this state. Now this is something we recognize because all of this combined is just a negative version of this Bell state that we also know to be this one right here. But notice that it corresponds to it having a negative sign in front. However, this still constitutes this state because in practice it actually just corresponds to global phase, which we can't measure. So like this is practically the same as just this state. Now, to be able to perform a measurement that looks like this, we actually also need to know how to implement it. Now, this is actually just like very simple, but if we want to perform a Bell state measurement, in the process we have to destroy the Bell state we are measuring. That's again an aspect of quantum mechanics. You destroy the system that you're measuring. Um, so if we imagine that we have our entangled qubits being sent into this measurement, we can express or like measure this by transforming the Bell basis into the computational basis at the cost of the entanglement, but it does produce distinguishable results. The way we do this is just that we perform a Hadamard gate on one of the qubits, and that qubit is C-naughted onto the other qubit. Now, for every Bell basis, it will produce, or like for every Bell state, it will produce a unique pair of computational bits, which is why it is distinguishable, which is why it allows us to even perform this measurement up here, which tells apart which unitaries Alice performed. Now, I should also just mention that if you want to switch back and forth between bell basis and computational basis, these like types of measurements, you can actually just do it by, oh, I messed up. Uh, Not this. Well, okay. The Hadamard gate is unitary, so if you apply it twice, it is the same as doing nothing. However, that's not what I meant to write out. What I meant to write out is if you conjugate this, so like just do it in reverse. So if you imagine, like if you want to undo this, you would just like mirror it, and you would go back to being in the same basis as over here, is what I meant to write out. Um, Now, the second type of protocol that you guys looked at was this quantum teleportation, which is actually like one of the reasons this is like so fascinating and popular as like a quantum phenomenon is just because of marketing and like framing. Because like in practice, this is actually just a quantum fax machine, but quantum fax machine sounds extremely lame, and quantum teleportation sounds sick, which is why it's so cool. But like, let's see how it works. So, in quantum physics, you can't copy a quantum state, and I'll get to why in a second, but for now, we just need to know that you can only transfer a quantum state from one element to another. Now, if we have Alice, and let's say that she has a quantum state such as this one right here, a superposition of computational 0 and 1, and she wants to give it to Bob. But the problem is that they are spatially separated from a large distance, and she can't really transfer her physically her system to him. But luckily for them, they share they each have one qubit from an entangled state from a previous meeting that they had. Well, they can actually use this entangled pair to transfer the quantum system that Alice has in her lab to Bob's. Now, the way that we do this is that Alice takes the quantum system she wants to transfer and her qubits from the pair of entangled qubits that she shares with Bob, and she performs a Bell state measurement. Now, from this Bell state measurement, she's going to get a unique pair of classical bits, which are distinguishable. Now, this will sort of like, I lost my train of thought. Let me get back. Um, Whatever the outcome of this Bell state measurement is, one of these four results, she's going to have to classically communicate that to Bob somehow. In other words, they make a phone call. So she makes a phone call with Bob, and she tells him, "Oh, I got 0, 0, or 0, 1, or 1, 0, or 1, 1," basically corresponding to the outcome of her measurement. Now, the way that Bob then receives this quantum state is that they sort of like encode these results into unitaries that Bob performs on his qubit from the entangled pair. So if Alice measured 0, 0, Bob would do nothing to his qubit. If she measured 0, 1, Bob would perform a Z gate. If Alice measured 1, 0, Bob would perform an X gate. And if Alice measured 1, 1, she would tell Bob to perform both gates. Now, after this protocol, Bob's single qubit will be an exact copy of Alice's quantum system, but Alice will have lost her quantum system because she performed a destructive measurement on it. Again, in quantum physics, you can't actually copy a quantum state. You can only transfer it from one system to another, but it's just like convenient for like a semantic, for like educational purposes to say, conversational purposes to say copy. But okay, this whole protocol just utilizes and consumes an entanglement and a quantum state to transfer it from one quantum system to another, even at large distances. Very cool. But now, why is it that we actually can't really copy a quantum state, which is the last thing that I want to cover? Well, it's actually because of this no cloning theorem. So we know that in quantum physics, we can't copy a quantum state, we can only transfer it. And the reason why is that we can actually have a proof, or like a very simple demonstration of it. So if we assume that there is this sort of two-qubit unitary, which does this like encoding, which takes a, if we have a 0, 0 state, it doesn't change it, sort of like the Z gate. But if we apply it to the 1, 0 state, it transforms it into the 1, 1 state. Cool. Now we have like a uniquely crafted unitary, which just copies a specific state and applies it to another qubit. Let's see how this actually works out. So if we imagine that we have a qubit, which is in a superposition, not the computational plus state, but what's it called? The plus basis. It's in the plus state, basically 50-50, 0 and 1. And we have another qubit, which we know is in the computational 0 state. And we apply our unitary to this pair of qubits. By the design of our unitary, quote unquote unitary, it's not actually unitary, but if we assume for the sake of the thought experiment that it is, it should produce this get right here, plus plus. Cool. Let's see how it actually plays out if we do the calculation. So if we apply the unitary to the state and we distribute it to each ket in the superposition, the unitary will not affect this, but it will affect this and turn this 0 into a 1 because the first qubit was a 1. As a result, we'll get, whoops, I should normalize this. As a result, we will get this state here, which you also recognize to be one of the Bell states. However, this is a problem because this Bell state is not the same as this state that we established that it will become earlier. So this is in fact just like a contradiction demonstrating that we can't actually copy quantum states once again. All right, I uh, I hope this was helpful, and again, send me any questions if there's something you didn't understand or if you're wondering about. But yeah, take care.